So I'm happy to introduce our next speaker, Mitra Koley from ISI Kolkata. So she will be talking on the Grosvenor deformations and FSingularities.
Okay, thank you. So am I audible?
Yes, you are audible.
So I would like to thank the organizers for giving me the opportunity to present my work here. So I'll talk about Grosvenor deformations and FSingularities. So this is a joint work with Professor Matteo Varron. So first I'll talk about what is called FSingularities. So it is known that when a ring is a prime characteristic, then the Frobenius plays an important role to study singularities. So from here onwards, all the rings we are talking about are commutative with identity and of prime characteristic. So first we'll recall the definition of Frobenius. So the Frobenius is a map from a ring R to itself, sending each element of R to its pth power. So one can check that in characteristic P, the map is actually a ring homomorphism. The next lemma shows that the Frobenius detects the simplest singularity. So it says that a ring is reduced, that is, it does not have any non-zero nilpotents if and only if the Frobenius map is injective. The second lemma says what Frobenius does on polynomial rings. So it says if R is a polynomial ring over the finite field Fp, then R is a free module under the action of Frobenius with basis 1x x squared dot 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 x power p minus 1. And this lemma can be generalized to arbitrary polynomial rings of several variables. More generally, it's a classical result due to Kuhn's that a ring is regular if and only if the Frobenius is a flat homomorphism. So now relaxing the flatness criteria in several ways. So various kinds of singularities have been defined. Altogether, they are called FSingularities. So in the picture below, I write several FSingularities and the relations between them. The first one is F-regular singularities. So it is closely related to regular rings. And then the second one is F-rational singularity, which is closely related to rational singularity in characteristic 0 via reduction mod P method. And then the third is a pure singularity, which is that the Frobenius map is a pure map. And then the fourth one is F-injective singularity. It means that the Frobenius action on the local cohomology modules supported on maximal ideals are injective. Now we see some examples of F-singularities. The first one is summands of regular rings are F-regular. In particular, all regular rings are F-regular, hence all other singularities. And then the second one is normal affine semigroup rings are F-regular. And the third gives a hypersurface ring, which is defined via the hypersurface x square plus y square minus z square, where k is the field of characteristic greater than 2, then R is F-regular. And the fourth example shows that F-singularity really depends on the characteristic. So let R be the hypersurface ring defined by x cube plus y cube plus z cube, where k is the field of characteristic greater than 3, then R is F pure if and only if P is congruent to 1 mod 3, but the ring is never F-rational. So this is a short overview of F-singularities. So now we move to what is called Grosvenor deformation. So I start with initial ideal, notion of initial ideal. Let S be a polynomial ring with n variables over a field K. So here we do not assume that the field has characteristic P. So the field can be any characteristic. All these things works, the definition and everything. So let a monomial order less than on S is the total order on monomials of S satisfying the following two conditions. The first condition says that the element 1 is the least element with respect to the order less than. And the second condition is saying that if UV two monomials with U less than V, then UW should be less than VW for every monomial W. It basically says that the monomial order respect multiplication by monomials. And then the second definition is what is called an initial ideal of I. So let I be an S ideal and less than be a monomial order on S. Then we define the initial ideal of I. The notation is in I, which is generated by the elements in F, where F is in I, where in F stands for the biggest term of F with respect to the monomial order less than. Then given a monomial order less than, it turns out that it is possible to choose a suitable weight order, and the weight order actually depends on the monomial order and the ideal I, such that the initial ideal with respect to the monomial order is same as the initial ideal with respect to the weight order. So where in Wi is the ideal, again an S ideal generated by in Wf, where in Wf stands for the sums of terms of F with maximal W degree. So let's see one example. What it's actually saying, that let less than be a graded lexicographic ordering with x1 greater than x2, and so xn on S. Take F, the polynomial, as x1 cube plus x2 square x3 plus x3 cube. Then in F is the biggest term, which is x1 cube. So now next, one might wonder that given a monomial order and initial ideal, why we want to go to the weight order and say, okay, with respect to that weight order, the initial ideals are same. So one advantage of taking the weight order is that the initial ideal of I with respect to the weight order can be seen as a deformation. So I'll see what does it mean by deformation. So the criteria, the first we'll do what? Take ideal in S, then I'll construct an homogeneous ideal in ST, just one variable attached. So let T be an extra homogenizing variable, then let F be a polynomial with homogeneous component Fj with respect to W. Then we define a W homogenization of F as a homogeneous polynomial in ST. So where D is the degree, the W degree of F, and then if we take any homogeneous component, and then I multiply suitable power of T to make it homogeneous of degree D. So that is multiplication here we have seen, and then we define the hom Wi is the ideal generated by FH, and where F belongs to I, and it's an ideal of ST. And it's called the W homogenization of I. So one note that, as I said, that each FH is a homogeneous polynomial in ST, hence hom Wi is a homogeneous ideal of ST with respect to the extended weight, where the weight of x1 up to xn is the same as w1 to wn, but now the weight of T, the extra variable, is given 1. So then we say that the ring defined by ST by hom Wi is called a Grosvenor deformation. And in the R, we have the following things, that R is an n-graded ring where the 0 graded piece is the field K, and T has degree 1, and again the Xi as degree Wi, and the degree of Ti is 1. And in R, T is a non-zero divisor, and R mod Tr is isomorphic to S mod initial ideal of I, and R mod T minus 1 R is isomorphic to S mod I. So here, what does it say? It's basically saying that the Grosvenor deformation is a flat family over KT, where the spatial fiber is R mod Tr, is the spatial fiber is isomorphic to S mod initial ideal of I, and the general fiber, which is isomorphic to S mod the ideal we started with. So now one might ask, so given S mod I, so why we want to consider the initial ideal of this? So generally, in order to study various algebraic properties of S mod I, so sometimes we consider the S mod initial ideal of I, because given a monomial order, initial ideal being a monomial ideal, it is much simpler to study than S mod ideal. And there are relations between various algebraic properties of S mod I and S mod initial ideal of I. So for example, see the following theorem. If I be a homogeneous ideal of S and less than be a monomial order on S, then the first is saying that the Hilbert function of S mod I is same as the Hilbert function of S mod initial ideal of I. In particular, they have the same dimension. The second one is saying that the depth of S mod I is greater equal to depth of initial ideal of I. Hence, when S mod initial ideal of I is Cohen-Macaulay, then S mod I is so. And the third one is saying the similar holds for Gorenstein. So if S mod initial ideal is Gorenstein, then S mod I is also Gorenstein. And the fourth gives a relation between the regularity. So it's saying that the regularity of S mod I is less equals to the regularity of S mod initial ideal of I. So recently, Conga and Barbaro proved that I and the initial ideals of I are much more related than the usual, provided that initial ideal is a square-free monomial ideal. So precisely they proved that let I be a homogeneous ideal of S such that initial ideal is a square-free monomial for some monomial order less than, then the depth of S mod I is same as the depth of S mod initial ideal of I. Hence, S mod initial ideal of I is Cohen-Macaulay if and only if S mod I is so. And the second one is that the regularity of S mod I is same as the regularity of S mod initial ideal of I. So in similar vein, so one might ask that what does it happen for FSingularities? So the precise question is, for which kind of FSingularities do you have that S mod I has those FSingularities, provided that for some weight order W, S mod initial I has those FSingularities. So in a joint project with Professor Barbaro, we studied this question, and we first see that this question has negative answers for F regularity and F purity. So first, the negative answer for F regularity. So consider the polynomial ring on 5 variables where K is a field of characteristic P greater than 2, then take the ideal to be the 2 by 2 minors of the following matrix written here. And then by a work of Anurag Singh, it is known that S mod I is not F regular. So it's worth mentioning here that this example is the example using that Anurag Singh proved that F regularity does not deform. And we consider the weight vector W as 6, 24, 6, 3, 1 of x1, x2, x3, x4, and x5 respectively, then one can see that the initial ideal of I will be the 2 by 2 minor of the following matrix, of this matrix. And it's a two-dimensional normal ring. So hence, by a classification results of Watanabe, we know that S mod initial ideal of I is F regular. So that is, we have given an ideal such that there exists an order such that in S mod initial ideal is F regular, but the ring we started with, that S mod I is not F regular. So this gives a negative answer. Now the next example is the negative answer for F purity. So let's take the same example, but now take the characteristic P greater than 3, strictly greater than 3. Then again, by the same work of Anurag Singh, one can see that S mod I is not even a pure. And in this case, we can find a monomial order. So take less than is the lexicographic monomial order with x1 strictly greater than x2, and then greater than x3, and then this is greater than x4, and this is greater than x5. Then one can compute the initial ideal. It is generated by the square field monomial x1, x3, x1, x2, and x2, x3. Since it's a square free, then by a result of Hochstar and Robert, it is a pure. So here also we have seen an example where S mod initial ideal is a pure, but the S mod I is not a pure. So this gives a negative answer for a purity. So the remaining two cases where F rationality and F injectivity. So we could prove a positive answer for F rationality. So we prove that if let S be a polynomial ring over a field of characteristic P and with n variables and take any weight vector W is like integral positive weight vector if I is an ideal of S such that S mod initial ideal is F rational, then S mod I is F rational. So this gives a positive answer, and then the thing remaining is the for F injectivity. So we do not have an answer for F injectivity, but what we could prove is that we have a positive answer for strong F injectivity. So strong F injectivity is the F singularity that fits in between F purity and F injectivity. And we prove that let S be a polynomial ring over a field of prime characteristic, and W is a positive integral weight order, or maybe weight vector is same thing, then I is an ideal such that S mod initial ideal is strongly F injective, then S mod I is strongly F injective. And then this theorem has a nice consequence. The first consequence is let K be a field of prime characteristic and less than be a monomial order on S, a polynomial ring in n variables. Let I be an ideal such that the initial ideal with respect to the monomial order is radical. Then S mod I is strongly F injective, and hence this is F injective. So the proof is easy. So let's see the proof quickly, that since initial ideal is radical, it is generated by square free monomials. Hence, S mod initial ideal is a pure by a result of Hochster and Robert. Then in particular, this is strongly F injective. And by our result, S mod initial ideal is strongly F injective, imply S mod I is strongly F injective. In particular, S mod I is F injective. So now we pose this question that we couldn't solve for F injectivity, which says that let S be a polynomial over a field of characteristic P, and W is a weight order, and if I is an ideal such that S mod initial ideal is F injective, then is S mod I F injective. So now we'll see that this corollary is very useful to see singularities of various combinatorial algebras. So here we'll talk about only two. So the first is singularities of binomial edge algebras. So let what is called binomial edge ideal is let G be a graph of, let G be a simple graph on vertices V1 to N, and let E be the edge set, let S be the polynomial ring in 2n variable, so x1 up to xn and y1 up to yn, where K is a field. Define the binomial edge ideal Ig is generated by the binomial xi yj minus xj yi for each. So where ij is an edge of E, and the algebra defined by binomial edge ideal is called binomial edge algebra. So let's see one example. So when G is just a triangle, and the vertices are 1, 2, 3. So then what is the Ig? So 1, 2 is an edge. Hence x1 y2 minus x2 y1 is in the ideal. Okay, and then 2, 3 is an edge. Hence x2 y3 minus x3 y2 will be in the ideal, and since 1, 3 is an edge, then x1 y3 minus x3 y1 will be in the ideal, and these are the generating set of Ig. And it is known that there exists a monomial order on S mod I on S such that initial ideal of I is square free. Hence, by our result, we can say that let G be a simple graph, then the corresponding binomial edge algebra is mod Ig defined over a field of prime characteristic is always strongly F injective. In particular, this is F injective. So this is the F singularities of binomial edge algebras. So next combinatorial algebra is algebras with straightening law. So here I will not define the definition, because I think Yeah, I'm running out of time. So I'm just saying that algebras with straightening law is an algebra defined on a poset which has a presentation. The generators are indexed by age, and the relations has some good properties. So the properties are these 3 bullet points. Okay. So and then the examples of algebras with straightening law are first the coordinate ring of Grassmannian, and the second we see that R is the hypersurface ring defined by x11, x22 minus x12 minus x21. So this is basically a determinant ring. It's a 2 by 2 matrix, and then the ideal is just the determinant of the 2 by 2 matrix. And one can see that R is the ASL with the following poset. So I write the poset here that x1 is the smallest, and then x12 and x21 is not comparable, and then x22 is the largest. And again, we show that if R is an ASL, that is algebra with straightening law over a field of prime characteristic, then R is strongly F-injective. And so it is F-injective. So I'll stop my talk here. Thank you for listening. These are the references. There's some references I would like to, Thank you. So.
Thank you, Mitra. So let me thank the speaker. From the audience. Yeah.
Hello.
Hello.
Am I audible?
Yes.
So could you please go back to the slide where you prove that, I mean, that non F regular case?
Yes. Here.
Yeah. So the initial idea here is not a square free, right? It's not square free, right?
No, initial ideal is the 2 by 2 minor, so it is not monomial actually.
Yeah, right. So yeah, right. It is not even monomial ideal. So
Yes.
So let's say if the monomial, I mean the initial idea is monomial ideal or like give strong condition that it is square free. So what happens in that case here?
So if the initial ideal is square free, so any square free monomial ideals is a pure. In fact, they are split.
Okay. Okay.
That's a famous result by Hofstadter and Robert.
Okay, and then F-regularity will hold, right?
Yeah. So that is the same there. As I said, like here we can say that this is like this thing, right? That x1, x3, x1, x2, x2, x3. But see, this cannot be F regular, right? Because S mod initial ideal is not a domain.
Right.
So but here we take that this is actually a two-dimensional normal domain. So the initial ideal. So we can talk about whether it is F regular or not.
Oh, okay. Thank you.
So any other question from online audience? Okay, so if not, let me thank the speaker again. And thanks, Mitra. So,
Thank you. So stop share.